Hi, everyone. My name is Alec Guertin, and I'm coming to you today from Android security team at Google to talk about reverse engineering applications. So a little bit about who I am and what I do. I work in Android security, specifically uh, looking at and investigating malware in the Android ecosystem. Um, so this means both on the Play Store, off the Play Store, pre-installed on devices. And my main role is reverse engineering applications and looking at new malware techniques and look and figuring out how to write automation to detect them. And before I jump in to any kind of security talk, I always like to add something to help boost people's moods a little bit. So here's a picture of my dog Sierra, seen here pretending to sleep so that I won't clip her nails. Okay, now that we've got something, a happy thought in your mind, I'm going to jump right in and start talking about it. So in order to understand kind of how I'm presenting this material, I think it's important to realize I'm coming at it specifically from a malware perspective, but when you reverse engineer apps, that some of the goals may not be the same for you, but whatever you're doing, this is a really great place to start. Whenever someone who's doing reverse engineering starts learning how to reverse on a new platform, they usually start by actually developing for that platform. So everyone at this conference really should already have kind of a leg up because you already have some experience with the Android framework and the Android platform. And so you've got one of the hardest steps out of the way. So even if for reverse engineering as a hobby or for work, your goal is actually to reverse engineer PC games or something, this can still be a really great place for you to start because it'll help you build skills and intuition, which will transfer to other platforms or other types of reverse engineering later. So the reason that our team reverse engineers apps, as I mainly said, was for malware. And to give you an idea, there's generally two categories we're looking at. One is things that directly put the users at risk, and we call this PHA, or potentially harmful apps. And the reason we call them potentially harmful is not because we're not sure they're harmful, but because they might not be harmful to all users. So an example might be something that tries to steal your banking credentials, but if you don't use a bank that they're targeting, it might not affect you. So in that case, it might only be harmful to users who have bank accounts with certain banks. They also might still be user-wanted apps. So, for example, you might have a browser or a game app that has an SDK that they're using that has some malicious content in it. But the app itself can actually still be useful. Our other category is mobile unwanted software, which may not strictly be considered malware, but they might still be harmful to the user or the ecosystem or other companies. So some examples of this might be things where they're stealing personal information that's not sensitive enough to be considered spyware. So, for example, we might flag something as mobile unwanted software if it's taking your phone number, but we would flag it as PHA if it's taking the contents of your text messages. And we actually track these separately. When we start reverse engineering apps, mainly we have some kind of reason to suspect that they're malicious or dangerous. So we actually get apps from a bunch of different sources, like I mentioned, like the Play Store, pre-installed, user reports, partner antivirus companies, and we do some kind of automated analysis on them. And then we score them to decide what the risk level is and why it's risky. So if we have a high enough level of confidence, we can go ahead and either just reject it and say it's malware, or we can say we're pretty sure it's not malware. But if it falls somewhere in the middle where we're not sure, but it looks suspicious, we might have to take a look at it manually and verify the behavior. Okay, so jumping into looking at APKs. So if you actually get an app, you get the APK file, it's really just a zip folder. So you can actually go ahead and unzip it and take a look around inside. And these are the things you'll commonly see. You'll see the manifest. You'll see the dex files that contain all the Java code. The lib directory will contain any native libraries you might be using. Resources contains a bunch of XML files and images. And then there's assets for anything that doesn't fall into the other categories. The problem with just unzipping it is that most of these files in their current format aren't really going to be readable or useful to you. So all the code is going to be compiled, and all of the XML files are going to be compressed. So the first step we can take to actually start poking around in an app is we can use something called APK tool, which is an open source tool that you can get. And two important things it does here is the first, it decodes all the XML files so that they're actually readable. So you can go ahead and get the decoded Android manifest, which will give you all the entry points, all the permissions it requests, all the permissions it defines. You can take a look at all the activities, receivers, services, things like that, any broadcasts it might be looking for. And you can also look at all of the strings that it uses that aren't just in the code. The second thing is it will convert the dex files into Smalley. So this is the disassembly, but not the decompilation. So the dex files themselves are optimized and compiled in a way that you're not really going to get any useful information just by opening them up or looking at the contents of it. But once you have the Smalley files, you can get something readable for each class that's defined in the dex. So here's an example of a Smalley file. So you can see it's definitely not as easy to read as Java, and that's a little bit more, I guess, verbose. But it's still somewhat human readable. So in this case, you can see at the top that the source file was originally smsbackupservice.java. And then you can see things like the static field that it defines in this class. And then there's an example of one of the methods right here. And so this can kind of give you a high-level idea of what this class does and what the code does. If you actually want to try and read this to actually follow the code execution paths, it can be very time-consuming. But it just depends on what your goal is, whether or not you actually need to go any further than this. So if we want to look more closely at the actual source code, then it can be useful to actually decompile to try and get back some readable Java code. So there's a couple tools I've listed here, which I really recommend. These are not the only tools, but these ones are all open source, so it's a good starting point. Dex to jar will convert the dex file into a jar file, and that'll contain class files, and from there you can use a lot more tools that are not necessarily Android specific, but are for reverse engineering Java or decompiling Java. JDGUI and is a tool for decompiling those jar files into something that's readable Java. My personal favorite open source is JADX, which is another GUI that will actually allow you to decompile straight from the dex to the Java, so you can skip the dex to jar step. The reason I list both of them here are just to give you options, and also because some decompilers will decompile things differently. Sometimes the things like switch cases may get interpreted as a bunch of nested if-else cases. And so some decompilers are better than others for certain types of code. And so sometimes if I'm using open source tools, I might actually use 2 or 3 different decompilers to try and get a better idea of what the source code may have originally actually looked like. Also, by nature of it being open source, sometimes things have errors, or they're not frequently updated right away for the newest versions of Android or the newest versions of Java. So it just gives you options. So once you get the decompiled Java, you can actually usually get something that's pretty close to the original source code. Tracking variables and things like that can be a little bit different than just opening GitHub repo and following the code paths. Um, some things I want to point out here are you'll see things like you'll frequently lose variable or class names. So if you look at the onHandle intent function or method here, you'll see the HTTP URL connection variable is just named v1 for variable one. A lot of times you'll lose the variable names for input parameters as well. Also, for things like static strings, decompilers usually can't tell when things that are static were referenced. So if you look at where it establishes or creates the new URL instance, you'll see the actual URL string there instead of the static final URL path variable. And so that's just some kind of inferences you'd have to make in order to actually get the original source code back. So it's not going to be exactly the same, but it'll get you something pretty close. And once you start getting a handle on what this code is actually doing, then you can start renaming variables yourself to make them things that are more useful for you. Some decompilers will allow you to rename a variable and it will rename it everywhere in the code. So it'll propagate or rename a class, things like that. Okay, so once you have your decompiled code, a great question to ask is where should I start looking? Especially with bigger apps, it's really easy to just start going down a rabbit hole. And so really it's important that you think about what's your end goal before you actually start looking anywhere. And how much background information do you have? You know, if you get an app from an app store, you might have a nice description. You might know something about the developer. But if you're getting an app that mysteriously appeared on your device and you don't know where it came from, or if you get an app somewhere from some link on the internet, you may not know as much about it. So starting just in the manifest is usually a good bet if you're not sure, because looking at all of the entry points like the activities and receivers and looking at the permissions will just give you a sense of what it's actually capable of doing. You know, what broadcasts is it getting from the system? Permissions that it requests lets you know what it can actually do. And if you start from the entry points, you're going to get, you know, what are the actual code paths that are most likely to be executed under certain scenarios. Another way that you could go is also just to look at strings that are defined in the XML resource files, or the Smalley strings, the strings that are defined in the code, and even images. They can actually just give you a better sense of, you know, what's the purpose of this app. You know, what kind of things is the user going to be presented with? So some cases of things that are useful for me when I'm looking at something I don't know what the app is for is, you know, I might find terms of service listed in the XML strings, or I might find images that suggest to me, oh, this is a game. Things that might give me some clue are also recognizable SDKs or libraries. So, you know, there are a couple SDKs that are really common ad SDKs like Facebook or Google. And then there's also common native libraries that might be used that for image processing or for games. IOCs here stands for indicators of compromise. So when we're looking at malware or something malicious or with vulnerabilities, often there are things that will tip us off that a specific app is from a certain known threat actor. So we might notice patterns across multiple apps from the same malicious actor, and we call those indicators of compromise when we know, you know, this is how we signature this app and identify to this user, and this is the kind of behavior it has with malicious. In our case, sometimes, you know, we're also just looking for anything that's off, you know, anything that just doesn't look normal. And in this case, volume really helps. Once you've gotten some volume under your belt and you can, you know what are normal development patterns across different companies, across different regions, across different industries, then you'll know when things just don't quite look right, and that can give you an idea of where to start looking. Maybe everything in the app is looks fairly normal, but there's one class in particular that has some weird strings or is abnormally large. That can also just be an interesting place to start looking. Another place that can be interesting to look is if anything is obfuscated or hidden in some way. So obfuscation is just pretty much anything that makes the code harder to read. And some of these things are not necessarily always used purposely to make the code harder to read, but can be used for efficiency. So like method and variable renaming, if you get an app where they use ProGuard or R8, then you're going to see methods and variables renamed to things like A, B, C. And that's not necessarily a sign that they're trying to hide what they're doing, just decrease their deck size. But there are also cases where you'll see something like this, where every method or every variable, every class is renamed to something that looks very similar and uses a lot of characters that are really similar. So in this case, you may not be able to tell, but some of those are uppercase I's and some are lowercase L's. Some are zeros, some are O's. And the whole point is just to try and make it harder for you to follow what the code is doing. Another way that someone might do this is by adding unnecessary or dead code to kind of throw you off and send you down that rabbit hole. You can also use reflection to hide what APIs you're actually using. So if I have some automation or a decompiler that gives me a list of all the APIs that are used, then it might miss something that's called with reflection because that API doesn't actually show up. They could just use strings to call methods. And one of the last things here is string encryption. So when you're looking at a class or any chunk of code, taking a quick look at the strings can actually give you a pretty quick idea of what that class or what that method is for, especially if log statements are left in, or if you can find comments or things like that. And so a lot of times you'll see malicious actors encrypt their strings so that you can't see what URLs they're using or things like that. So some examples might be some really simple things like just base64 encoding the strings. So in this case, this one just says droidCon 2020 when you base64 decode it. Another example is if you're trying to hide from automation, and I don't want someone writing a script that parses out the strings and analyzes them, then I might do something like this, where I actually store the string as a byte array of like ASCII values and then convert it to a string at runtime. Or I might do something like this, where I split up the string so that if I'm grepping over the code for the word droidCon, it wouldn't come up because here it's actually split into two separate strings in the code file. If I'm actually trying to make it harder for the person to read and for automation to get it, then I might want to do something more traditional like XOR encryption or AES or a number of other things. Some decompilers or some tools will actually allow you to write a script that goes through and does some kind of computation on the string, in which case you can maybe write a Python script that goes through and changes all the strings in a code file and shows them the new ones in the decompiler. But in general, I would start by just taking a look at a few and doing them manually. So CyberChef in particular is a great open source tool from GCHQ, and you can just run it in the browser. And it's a click and drag interface where you can specify what steps to take on the input or output. And so in this case, I'm just base64 encoding the string Android, and it gives you the output. And then once you're sure that it's interesting, then if you want and you have a lot of strings, then you can go ahead and write a script to do it for you. So this is just an example from a real app where they were actually using some kind of static method to do decryption of strings at runtime. And so here you can see it's base64 encoded. I think in this case, it actually also did some some other decryption on top of that. And they were using it to hide what method names they were using and then passing that to the reflect API so that they could call a method. And so in this case, even if I looked at the strings, I wouldn't know right away what method they were calling. On top of those obfuscation techniques, there's also packing techniques where they actually not only are trying to hide what the code does, but they're trying to make it harder for you to access the code. And so some examples of this would be when code is encrypted. So you might get encrypted DEX files in the assets or that are stored off device and downloaded at runtime. And then they would use like DEX class loader to load these and use reflection or something to call into it. Another way they might do this is there are libraries that you can use that are basically local VMs or interpreters where they interpret some sort of bytecode language, kind of like a mini processor in your app. And usually they do that to unpack or download the DEX file, not to actually run the whole content of the app, because that would be slow and expensive. And before I go on, I just want to mention one thing that, I want to talk about obfuscation and packing because it's not necessarily an indicator that the app is malicious. There's a lot of reasons to use this that are legitimate, like if you're in the finance industry and you don't want people hacking your app, or for gaming, doing DRM. So packing itself is not necessarily an indicator it's bad, and it's something you may run into even if you're not looking at malware. Another thing you might come across, and hopefully this will save you some time, is things where they're trying to do cloaking. And so by that, I mean trying to hide its behavior either at runtime, usually at runtime, actually. So things where they're looking for like when they're running in an emulator. And an example of why they might do this is because a lot of times we run malware in emulators because we don't want them running on a real device and corrupting a real device. They also might do this because ad SDKs don't want to be showing ads in emulators because they only want to be showing ads to real users. Malicious actors will also do things like waiting for a day or a week or more before they actually start doing the malicious behavior, because they know if an analyst launches it on a test device or in an emulator, then they're probably only going to be running the app for a few minutes. And so if they wait longer to do that bad behavior, they can avoid that dynamic analysis. Some of these other things here, refer based, you may only want to show advertisements if your app was downloaded from a certain app store, or if it ended up on the device in a certain way. And you may want to avoid being analyzed if you were sideloaded manually. They may also only want to show ads in specific regions, or do certain behaviors in specific regions or on certain types of devices. And malicious actors will also use environmental factors to try to determine whether or not they're on a real device. So doing things like looking for Facebook or Instagram, or looking at when the last time you updated your phone, or if there's a SIM card installed, what country you're in. All these kind of checks are usually indicators that they're trying to only execute that behavior in a certain environment. So this is an example from an actual piece of malware, which you can find on VirusTotal at this link, where they were checking if they were on a Google device. So basically, if the manufacturer was Pixel, Nexus, Google, and only then, if it was not on a Google made device, would they hide the app icon and launch a pop-up for you to try and get you to rate this app. There's also some interesting articles you can read about cases of cloaking here from some other antivirus companies. The first one's a case where they were trying to monitor your accelerometer data to see to determine if you were a real user. Because an emulator or a test device might not have any accelerometer or any interesting data anyway, as a test device will just be sitting on a desk. But if you can see if the person's walking around, turning the screen on and off, using other apps, then you can have a better idea of if you're on a real user's device or in a lab somewhere. And the second one is one where they would download a DEX file that did some kind of cloaking, and then once they were satisfied that they probably weren't being analyzed, they would download the next stage, which did a different type of cloaking. And they actually had multiple stages of downloading DEX files, and each one would download the next. It was kind of like a nesting doll. Okay. Getting a little bit more complicated. For developers, you've probably used JNI or the Java native interface at some point. But I want to cover here a little bit, just a few tips about reversing it. So JNI is just a way for you to call back and forth between native code written in C or C++ and Java. So you can load, on Android, you would load an ELF file, the Linux format, and you can call into the native code from Java, or you can do the opposite. If you really want to read more about the specification of how it works, there's the link on Oracle's website. But here's a really basic example, the source code for it, where we call system.loadLibrary in Java, and it looks in the lib directory for something called libnativelib.so, and it'll load that, and then anything in Java that's listed as public native, it will look in the loaded native libraries for a method that's matching that name. So by default, it will follow this format where it starts with Java and then has the full package name and class name and the method name. But that's not the only way to do it. So the first thing that's run when you load an ELF file is the JNI onload. But there's also an init array field that you can look at that may have function pointers to other things that are run. So when you're taking a look at the ELF file, these would be the first two places to look for the entry points into that ELF file. Calling back from C to Java or C++ to Java, you can use the JNI environment object to actually do something similar to reflection, where you're getting classes and methods and things by name, and you get that object and then you can execute it. So there's some examples here of getting the system service for the phone and then getting the SIM operator from that. And it's much more verbose than if you were just to do it straight in Java. But if you need to use that in the native code, it can be useful. And if you're trying to hide what you're doing, it makes it a lot harder to read. And when you want to go about starting to reverse native code, there's some options for you. If you have some familiarity with reverse engineering or security work, you may have heard of IDA Pro. I didn't list that here because I think there are some options here that you could use that won't cost you any money. So Ghidra is probably my personal favorite on this list anyway. That's an open source tool developed by the NSA. If you trust them to download it, you can go ahead. I did so. And the UI looks something like this. So on the left, we have the actual disassembly. So that's the actual ARM code, ARM assembly code, but it does have a decompiler. And then you can also do a graph view. So the decompiler is in the middle and the graph view is on the far right here. You do have to take the decompiler with a grain of salt when you're looking at native code, though. It's really best effort and shouldn't be taken as a source of truth, just as getting a general idea of what the code's doing. The decompilers here do make mistakes because compiling the native code is much more optimized. It gets a lot more abstract, and it doesn't convert one-to-one as well as decompiled Java does. So if something doesn't look quite right or something looks really complicated, I recommend keeping the assembly code open on the side as well. And when you're starting with native code, I find it much more useful to start with strings usually, or with methods, rather than some of like this more high-level skimming methods I talked about for the dex file. Okay, so I want to go over a couple examples that I just thought were interesting to throw in here from real malware samples. So in this case, they were doing some obfuscation using JNI, where they had a Java service with a public method, and they hid all the malicious code in the native library because the native code is generally harder to analyze, or generally harder to do automation to detect than Java is. So all they did here was they they put all the malicious behavior in the native code, and instead of using the default mapping that I talked about, where it would do Java, the class name, and the method name, in the JNI onload, they registered their own mappings for the Java methods to native methods. So even for automation, it makes it just that much harder to do the mapping to figure out what native code is being called from Java. Another example, and I swear they actually did call it com.swift.taylor, is this kind of multi-stage step using native code. So you can see they have a class here, a service called service Taylor, and it has a number of native methods, and they load the library and then call one of the native methods here, service Taylor _C. And so calling into that library actually de-obfuscated itself. So the native library had encrypted strings, but when it's launched, it decrypts all those strings. And then once it's done that, it decrypts 2 asset files. And one of them is pretty much solely for the purpose of persistence. And so a lot of times malicious authors will want to have their code running as much as possible so that they can monitor you or keep doing their malicious behavior. So in this case, the second asset here was an executable that just launches the same service again. And so it ends up in a loop. The service launches the executable launches the service, and this way they can stay running. The other one was another APK that gets dropped that has had a rooting exploit in it. And so in this case, they could drop another APK and then make a request to their backend server to actually get a rooting exploit. And so all that was hidden. And when you look at the code, or when you look at the original APK, it doesn't actually do anything interesting other than loading these asset files. So you have to do a lot of work to figure out what it's actually doing. So I didn't talk about dynamic analysis because for getting started, I really just recommend just going through the source code, decompiling, trying it out. I think all those tools there are plenty to get you started, and are a lot of work just to get used to. Once you're comfortable with that, then you can start taking a look at dynamic analysis. So you can do things like hook method calls, get them to return what you want, check what the output was, run things on an emulator and look at the system logs to see what APIs were called. You can set up a proxy so that you can try and look at what HTTP requests are being made, or sometimes FTP requests. And these are all tools that you can look up to get started for that. So just to wrap things up, just remember, don't be afraid. Like I said, you've already got the hardest step out of the way of just being familiar with the Android platform. So go ahead and give it a try. Pick something fun. You can find applications to reverse, anywhere. If you want something, more security related, you can find applications from blog posts from antivirus companies. You can find them on VirusTotal. There's a lot of different places if you just start looking around. Just remember not to download them on your personal phone. You can also take a look at CTFs, capture the flags, which are kind of a way for you to do it in a more safe environment and competitive. Google even has some where there will be Android challenges. And you can try reversing an application that you developed, and that'll give you an idea of, what changes when you decompile something. How different does the code look from the original source code, or how well is your own obfuscator working if you're trying to use a DRM for something. So yeah, with that, good luck. And if anybody has any questions, I think we still have about 3 more minutes. Okay. Since it takes only a few commands to get to the source code, what would you say is the most secure way of storing API keys in the app? Oh, this is a good question that comes up frequently. I don't know that there's a general way that I can really recommend. I think in general, hopefully the API that you're using will provide a way or a tutorial for you to do it. I would say, generally speaking, plopping it in the manifest is the easiest way for it to get found. But sometimes that's what they tell you to do. So hopefully, if they're telling you to do that, then I guess hopefully it's not a monetized API. But yeah, I don't have a good general solution for all cases, I'm sorry to say. Okay, the first and obvious: when is it even legal to reverse engineer someone else's code? That is also a great question. So if you're doing it on behalf of a company, I should preface this by saying I'm not a lawyer, and so I can't give legal advice here. But generally speaking, I think if you're doing it for your work, I would, check with your legal department first. If it's for personal use, usually I think you should check the terms of service. If you're downloading malware samples, I think that's a good place to start because, I don't think anybody's gonna be mad about you reverse engineering malware samples. And they're things that have already been reverse engineered and you can find information on. In your experience, are non-native frameworks, Flutter, Xamarin, Ruby Motion, etc., often used for hiding behavior? I would say I don't think they're usually used for hiding behavior. Sometimes it can be harder to reverse engineer, especially if you're not familiar with the framework. But I would say the most cases I've seen around these and malicious behavior is when people try to impersonate it to avoid detection. So you might see something where, they call all their class names like com.flutter.something, and they try to even make it look like the original SDK, but they'll add in some malicious behavior to it. APK comparison tool doesn't work for signed APKs. Any work around for this? I haven't used APK comparison tool. I'm not sure which tool they're talking about actually. I've only used my own tools. But generally speaking, I would say maybe try doing a comparison more on the DEX files. And if you use APK tool to get the original Smalley, then you can do a one-to-one comparison of each class, actually. Have you ever looked at COVID-19 tracking apps? Yes, this is something that we have looked at. It's something that we try to make sure at Google that these apps are secure and safe to use. And that's one of the reasons that we had this API that we were helping people, or we developed to help make COVID-19 tracking apps safe, so that they could just use our API to build their own apps. How to extract the signed APKs and DEX files. I'm not sure I quite understand what this question is asking. Are they asking how to extract it from the app, or from the device? If you're trying to get it off your phone, I would just use ADB and do ADB pull, and get the original APK off of it. And then I think I mentioned, to get the DEX files, you can just unzip it. It doesn't matter if it's signed. How would you reverse engineer .elf files? So in the case where they're libraries, like I mentioned, I would really recommend starting with JNI onload, and with the init array, because that'll give you the entry points and will tell you if they did their own custom mappings for Java to native methods. If you're looking at an executable, not necessarily in the Android context, or maybe if it's something that's pre-installed on the system, then I think doing things like readelf, or just even running strings on it and looking at the strings in it, trying to figure out if it's got symbols, things like that, and then popping it into Ghidra and looking at the points that are interesting to you for whatever your use case is a good starting point. Is an abuse of reflection a red flag? It can be. So, I think usually the more legitimate case of reflection that I've seen is when code is loaded dynamically and they want to call into a new DEX file or something. But even that, I think, can be dangerous, especially for us. For the Google Play Store, we don't allow dynamic coding, or dynamic code loading. So downloading DEX files and executing them, because it's too easy for the behavior to change, or for things to go wrong, or in some cases, code is downloaded over HTTP, and so it could be hacked where you're not loading the code you think you're loading. But there are some, I guess actually there is another legitimate use case, which is sometimes when I'm looking at pre-installed applications, they might use reflection to call into framework APIs, particularly if they're non-standard ones that are like specific to an OEM. But if they're calling a known API that's normal, then usually I would say that might be a red flag, because or at least a good starting point for me to look at what they're doing, because usually they're only doing it to do something sensitive. Where do I find a well-known PHA? Question 2: how do I keep it from trashing phone? Yeah, so if you're gonna run an app that is PHA, I would not recommend putting it on your phone at all. I would say load it in your emulator, or if you have a cheap phone or an old phone that you don't need anymore and doesn't have any of your accounts on it, then you could use that. Yeah, I would never load known malware onto my personal phone, though. And like I said, I would start, especially when you're first starting out, start with just static analysis, unpacking it on your desktop. Yeah. Question about API keys again. I don't know that I have a good resource. I know there's a couple folks from the AOSP security teams who are at the conference, and they had a roundtable yesterday. And so if you message them on, what's the platform called? Talc, I think, right? You should be able to message them on Talc. I think they would actually be better people to turn to ask about API keys. I'm sorry, I can't give a great answer for that. Need a way to generate and store a key for securing the database from storing a secure file, but is there a better way? So generally speaking, if you're encrypting something, I would never use a hard-coded key. if you do need to encrypt a database or a file, take a look at the Jetpack security libraries. It makes it really easy to generate keys dynamically and store them securely so that only your app can access it, and that's even not accessible by the user. And so I think if you go on the developer site for Android, there's some tutorials for setting this up. How to decompile, extract the assets files in user-readable format. So the asset files can be anything, really. So there's not just one answer. They could be HTML and JavaScript. They can be text files. They could be JSON. So it really depends on what they are. More specifically, I think if anything's compressed XML, then APK tool should automatically take care of it. If it's encrypted in some way, then you probably will have to look into the source code to figure out how it's decrypted, in which case CyberChef, the tool that I showed earlier, actually allows you to upload a file to run through the algorithm that you've defined. And so if it's encrypted or encoded in some way, then you can just do that, or when in doubt, turn to Python. How can we reach out to you if you have any further questions? So it depends what the question is. So on the first slide, I put my Twitter handle. If you're just interested in chatting or asking some basic questions. If you have something you want to report, then you can go to the Android security website and actually file a formal ticket that'll get handed by our incident team. Yeah, it looks like we're out of questions. So thanks everybody for coming out.